All right. Mary?
Yes, sorry.
Perfect. Hello, everyone, again. Hello, everyone who've been at my talk, the quick one, just before this session. And hello to everyone who just came, who is new one at this room. All right. Today we are going to talk about machine learning. We are going to talk about reactive streams in the context of multiplayer Pacman game. All right. Before we're going to start anything, we want to define for whom this talk, just in order to let you understand what will be in this talk, and just in order to let you switch to another session just in case you are not interested in these particular things, because this is valid. We are caring about your learning, about your new knowledge. So it's important. Right. Basically, this talk is for newbie in machine learning and artificial intelligence. So if you're curious about these things, please welcome. But please remember, we are not an expert in this topic. I know something about reactive streams. Mary knows something about machine learning. So together we will be trying to explain some basic things about machine learning and AI. And of course, we will be showing some coding approaches and how you can apply reactive streams in order to combine machine learning in really clean and efficient way with in distributed system. So this is basically the topic which we are going to cover. Is it sounds good for you?
Yeah.
Perfect.
So, yeah, in some ways it's an interoperability type of topics that kind of cross over two different subjects, essentially.
Right.
So, yeah.
All right, then let's start. My name is Oleg. I work for Netify. I know something about reactive programming, reactive streams. I love this topic. I have contributed to Project Reactor and still continue doing that. And I'm working on RSocket project, which I just explained it to many of you. And we'll be showing some demos with that technology as well. Today with me is Mary. Mary is from IBM. Mary, please introduce yourself.
That's right. So yeah, my name is Mary Grygleski. I'm a developer advocate at IBM with the Java developer advocacy team. So my specific area now includes like reactive programming and reactive systems. I'm also the Chicago Java Users Group JUG president and also like board member. So if you come to Chicago, let me know and visit our JUG as well. So. And then I just want to also add a note to how you may be wondering, like, how come like myself and doing from Chicago and then meeting with Oleg? It's because I was at DevOps Ukraine and I met Oleg and he was like the most wonderful host. And so anyway, so we decided let's do some talk together on reactive this topic. So.
All right. So during this presentation, we are going to start with this definition why Pacman in machine learning context. Then we're going to talk and explain different machine learning approaches in order to solve our particular problem, and how reactive streams and reactive programming are fitting into this particular domain. That's basically what we are going to do during this talk. And yeah, we will see how to apply this technology. All right. Basically, why Pacman, Mary?
That's correct. So why Pacman, right? So Pacman is a very popular game, arcade game, since the 70s. I'm sure some of you, or most of you are aware of and have played a lot. And like myself too, I was growing up and playing that too. And then also the fact that it has a very undeterministic kind of behavior of the ghosts, of the Pacman, it basically make it kind of perfect candidate for like illustrating, like training, like applying machine learning algorithms and train the bot. And it's really good field for AI and machine learning research. And then it's really from a computation perspective, it's actually easy. And I guess it's easy for learning purposes. It's kind of simple. We can leverage that to explain the rules in AI and machine learning.
I suspect that we don't have to run a cluster of machines in order to run this simple game. And we can just get some results just running this simple application on my laptop, for example.
That's correct,
Oh,
yes.
yeah.
So, yep. So now, because of its popularity, there's actually still competition going on too in the world. And if you look into this, this is a competition that we found out is a Miss Pacman versus Ghost team competition. It's basically inviting people to design like better and better and faster algorithms. And this particular one came from 2018.
But I'm wondering, okay, since we have already got tons of solutions, there is a competition on some predictable environment and some predictable game with set of levels, why do we have to spend some time looking into that area?
That's right. So basically, you're wondering, yeah, why is it is there all the problems solved? We're already playing the game. Now, the thing is, nowadays computation is more complex, and the fact that we can be playing this game from remote and not just from one machine, like from multiple machines, from like remote, everybody participating, multiplayer distributed environment. And of course, too, I've seen your multiplayer Pacman that demo too in one of your talks, and that's how I got very interested. I said, well, there's got to be even better way of solving this problem.
So yeah, okay, let's first quickly explain what I've done in my previous demos of multiplayer Pacman game, and let me quickly explain what's going on inside my solution, basically in order to let you understand what's going on and what kind of context we have. First of all, I created a simple client-server application and browser application, which means that we have to have server running on some port. And of course, if it's browser application, we have to be able to serve some user page with some information on it. So basically, we are loading some page. We're using some push technologies and so forth and so on, like asynchronous. You are not pulling data. You're getting all information asynchronously from server side. And server pushes everything, including, for example, tails. Then the next interaction that we have in our simple game, we have kind of setup. So you as a user came to the web page and saying, okay, this is my name, I want to start playing. And the server returns the current state on the desk. Then it created the most simple implementation ever. So in order to start moving your person's Pacman and Ghost, you simply have to update your location on every step. This is the most dynamic and straightforward solution that I ended up, but it works, right? And on the other hand, server provides the same updates from its side. So all the players stream the information to the server, and then server streams some information, for example, like location updates back, along with some important updates on, for example, score. So we are receiving a stream of location updates as well as score updates, and in this way we are going to play pretty interactive distributed game, as well as trying to compete other players, right? So the implementation is pretty straightforward and does not require, for example, information about rocket science or knowledge about rocket science. All right, let me quickly show you what's going on within this game. So you are all welcome to join and play with me. Let me quickly do that. And you can simply, okay, let me, yeah, most probably have tons of links. Yeah, it doesn't matter. Yeah, let's open one, follow the link. Okay, network. All right, something went wrong. Let me try to not, yeah, right now it's working, perfect. So if I'm going to enter this link, let me share the QR code again with you. You will be able to join this game. All right, I'm not alone, perfect. You're playing. And you will be able to move your character, your Pacman or your Ghost. In this case, we are all Ghost because basically we don't have any Pacman, because our goal for this presentation is to train a bot or agent to play with other Ghost players. That's why we are just Ghost and there is no Pacmans. All right, let's go back to our presentation and let's question in, basically you, Mary, what machine learning approaches do we have today in order to write a bot and agents that can play with real players?
Sure. So let's take a look at a few kind of more popular machine learning approaches that we can use for like the Pacman controllers. So again, bear in mind too, we're not machine learning experts, but we have done some research in order to basically build up this use case. So we'll discuss a bit. So first of all, there's the rule-based approach, and then these are like essentially the ones, but we'll go like one after the other, have some quick kind of introduction. So rule-based essentially is like utilizing like if-then controls. So basically, it remembers all of the action that it has taken. So basically, then it will then do certain moves. For example, you're moving right or left, and then if you move right and there's a pill, you eat it, things like that. So you kind of have to know your domain knowledge quite well, know your domain well, and then be able to kind of essentially build up this knowledge base in there. So if you can think about it, if like every single move, like kind of statically, you need to know that, particularly in the environment, you need to remember, where you are and what is the state, and then the environment and everything. So you can imagine, it actually does require you to know everything kind of ahead of time and kind of, kind of know what it is. But the thing is really predictability.
Yeah,
right?
I think it's not gonna fit into our case because we have like a totally evolving environment. Every time we have new player or connected and disconnected player, and most probably we will always change the field in which we are playing or map at which we are playing. That's why this kind of solution is not going to be really well for our case.
That's correct. So let's take a look then. Another way of doing things would be like using a Monte Carlo tree search method. So it's basically your analysis on the most promising moves, and then basically expansion on this search tree, and then like you basically still have to do a lot of random sampling of in your search space, and in that case too, in order to derive at your knowledge base, build up something that's useful, you do need to have also a large amount of data sampling.
So as I understand, you're generating an array or like a stream of actions before you start playing, and then trying to apply this stream of action into your particular round, right? And then figure out whether this generated random number of action is good enough or got a higher score, right? That's what I'm understanding from what you explained. But again, from my point of view, it sounds a little bit to require some predictable environment. And again, since we have changing or an evolving environment, it won't be possible to apply the same generated number of actions to learn and increase knowledge of our agent and bot.
That's correct. So in the anticipation of move, that will be kind of the key of like why it may not, it still like falls short. So let's take a look then at another algorithms, which is evolutionary algorithms. So as such, it's based on genetic programming and based on the grammatical evolution of your syntax, the grammar. So that too also requires you to have quite a rich set of domain knowledge, though it isn't as like heavily required like the rule-based, kind of pure rule-based kind of approach.
So as I understand again, it's something similar to Monte Carlo case or approach, but again, we are generating set of action, try to apply it, and then try to evolve, trying to, for example, fork from existing set of action and create another subset of action in order to make sure that this subset of action is a little bit better than the previous one. And because of that, we are growing and growing in the number of forks, and after that, it's became kind of tree.
Correct, yeah.
And that's why it's evolutionary.
It's evolution,
Yeah.
That's right. So you still need to kind of know kind of enough and then build up quite a large base. And you can actually run out of memory too. So anyway, so let's take a look then. The next step up would be like an artificial neural networks. So
Sounds complex.
Yeah, that's right. So as such, right, I mean, I'm not a neural network specialist, but let's say if you look into here, I was trying to like summarize, you can see even the words are kind of complicated. You're dealing with computational abstractions and dealing with how your neurons work and how the human brains work and some universal functional approximations. So you essentially, too, with that knowledge, you have to configure and then build up your policy networks, too. So as you can see, it's actually quite complicated, and then you also have to like know the game state and then apply these policy accordingly and everything. So basically, as such too, it's like you're trying to learn some optimal like playing strategies after being trained over time. Like in some sense too, it's like reinforcement learning. You're kind of going back and feed it back, and then let your bot kind of learn the situation. So.
Yeah, sounds a little bit complex, and looking at this picture, I can't understand anything. So
at least,
yeah.
That's right. So just show it to you. As you can tell, right, it's very computational intensive as well, and all the theories, all the formula you need to apply to it. So, okay, so without that, let's also take a look in the math in actions too. If you simplify a little bit, essentially too, you have input, and then you go into also like processing and gathering, pass through some bias like a function that basically eventually you go through an activation function and then output. That's what it comes out is your outcome of a certain kind of.
All right. In any case, it sounds too complex and require too high mass knowledge, and most probably, let's skip this one.
That's right. So now, okay, let's also take another one. Is more like a neuroevolutionary approach. Essentially, it's a hybrid between like the evolutionary algorithms and neural networks that we just talked in the previous 2 slides. And basically, it's using evolution. It's basically evolve the weights, evolve these topologies, and basically based on that, there are some reward functions that you can use to kind of generate your outcome and all the predictions and everything. But even with that, again, we go back to how kind of complicated, right? We have to kind of solve this Pacman problem. So then we kind of talk a little more, and then we found out, oh, there's this reinforcement learning and Q-learning approach. As such, too, it's based on, it's a bit simpler in the sense that we have the decision, we have the components, and also a knowledge base. 3 main kind of component, and basically from your outcome, you kind of build up your knowledge base. And then it's a progressive learning model and doesn't require a huge domain knowledge because it's dynamic, you're learning as you go.
Oh, this is something which can really fit well into our case, because if you're saying that this is an evolving or evolutionary approach and it doesn't require you to have a huge domain knowledge, then we can easily use it for multiplayer environment, evolving environment, always changing environment without any problems, right?
That's correct, and that's what we can explore.
Can you explain a little bit more about this approach, please?
Sure. So as such, reinforcement learning, again, there are like 3 main parts to it. The decision. When action comes, you need to make a decision, and there's an outcome. And also then from the outcome, you basically build up your knowledge base.
So let's stop a little bit more closer on every step in order to ensure that everyone understands what's going on.
Okay, so yeah, essentially too, in any reinforcement learning scenario, you need an agent too. So basically action comes and then the agent will then basically look at your action and make some decision. In this particular case, let's take a look. In any kind of game, when you start, there's no knowledge base. So your initial decision is a kind of random kind of decision. In this case, like for example, your Pacman, you can go right or left. So those are the 2. And because there's not already some sample kind of build up in your knowledge base, so you basically then make a move, then you do a move, and then here, one move, you know that you eat a pill, then you kind of gain the points. In this case, what you do is that while there's no goals in here, you gain a points, then basically you add 10 points to it. And then as you can see, your scoreboard here, it goes up. Let's say you're 85 at this point, you gain 10 points. So that's like the outcome that you have.
So in that case, it's positive outcome.
That's right, it's a positive outcome. So it's a reward-based system, so it's a positive reward, so you get the reward. And from there, then you essentially well, let me see. Yeah, okay, so your decision, again, you build in, you add 10 points to your outcome. And that's what it builds up into your knowledge repository.
So basically, it means that in order to gain knowledge, you have to make a move, for example, some action, which is decision. Then you have to observe some outcome, which is in that case like positive outcome. And based on these 2 states, you combine some knowledge about this particular number of pills and this particular state and position of player and this particular action.
That's correct.
All right, so what happens next?
Okay. So in this case, well, what will happen is that then you continue, like in your game, you move. So every move to what happened is it will check to see if it's already been stored, your particular action and the outcome. And basically, you can reuse the knowledge if it's already there. If not, then it will again be like a random decision. And then based on that, then you slowly build up progressively, like learning and build up your...
So basically, it means just in case we end up with the same state, for example, with the same number of pills on the map, with the same position of our Pacman, then we can go to we can call our knowledge base, try to find the same state as we've done before, and try to apply existing knowledge into the same state in order to gain, again, the same benefit, right?
That's right.
All right, this is simple, so sounds pretty straightforward.
That's right. So,
however, I'm seeing one problem here, or even not one, but a huge problem. First of all, as I understand, we have to collect the whole state, right? We have to collect all the whole position of the pills on the map. We have to associate the position of the Pacman, and then to this whole state, which we have to somehow encode in the number. We have to add, for example, the reward and then we have to apply only the same position of peels and Pacman in the same state. So it's impossible to use this knowledge in different cases. But even more, since this is always evolving environment and we have different number of ghosts connected and disconnected, and for example, map could easily be changed, we can't fit everything because we would have to generate more and more knowledge, learn, and we won't be able to reuse something else. And basically, it continues evolving and growing number of knowledge base, which would lead to most probably out of memory because our computers, our existing environment is not infinite or super elastic. We have some finite number of memory, like runtime memory or driver memory. So this is a huge problem in particular our case. So do you know how to solve that problem?
Sure. So now, as we're doing research, we found out there's actually an improvement over the reinforcement learning approach, which is using case-based reasoning. As such, case-based reasoning is also used in the law system too. So you're basically like identifying some scenarios. You're learning new things, but you're also like learning certain repeated kind of patterns that you keep in mind. So the difference, you may be saying that, well, you're learning, so it's kind of like a rule-based, but the thing is too, between that case-based reasoning and rule-based, there's some difference. Case-based reasoning is more like a lazy generalization. That's what I'm finding out. Because in a rule-based, you remember everything. For example, you're making pancakes, in this case, right? You're making pancakes and then you can be making just pure pancakes, or you're making blueberry pancakes. But the rules, too, is that in normal rules, you may kind of remember how to make blueberry pancakes. But when you do plain pancakes, then it probably doesn't quite remember, and then you have to kind of figure out what to do. But in a case-based scenario, is that you make pancakes, and it remember how you make pancakes, it remember that, but the blueberry may be something extra. Then it will then kind of store it as extra. So in some ways, it's a more lazy generalization.
So as I understand, it's kind of you're building a pattern, or you have some understanding on some pattern, and then you can reapply the same pattern for a similar cases. So if you know how to do pancakes, you can do pancakes with blueberry, for example.
That's right, something like that. So there's an advantage.
Yeah. So how we can apply then this on key learning and reinforcement learning case?
Sure. So as such, right, case-based reasoning, you have a knowledge base. Basically, what it is doing, again, is finding some similarities between like your, certain actions and what you're going to be doing. And basically using this KISS rule, keep it simple type of rule.
So in that case, you don't have to have the whole state of all the peels and all the players. As I understand, you collect like this pattern. You're looking for the closest peel on the top, on the left, on the right, on the bottom, and then you use this particular state as a kind of key for finding similarities with difference.
Exactly. So that's like the key of that. So in this case, yes. Again, too, it goes back to it's an improvement over reinforcement learning, too. It's not something new to it, but it improves over that.
So basically, you're using the same, you're basing case learning and then reinforce knowledge base that you already have at runtime.
At runtime, that's correct.
That makes sense.
Yeah.
So let's summarize what we heard. Basically, continuous learning with reinforcement learning is a good solution, as we have seen in our particular multiplayer case in Pacman. And case-based reinforcement learning can easily solve the problem of infinity growing knowledge base. So we can have a finite number of knowledge on our disk or in our runtime memory, and that's it, and use it for playing other cases. Sounds good. It means that right now we can easily apply a reactive approach to build this agent and connect it to our multiplayer Pacman server.
That's correct. Combining reactive streams, I believe it should kind of have some benefits. Can you tell us more about it? Why reactive streams?
Yes, so this is a good question. Basically, if we're gonna think about Pacman and how we are controlling our Pacman game, we will see that we are doing simple action. And again, in essence, we are generating some movement up and down. And it's pretty similar to how we are doing, for example, mouse moving or typing on a keyboard. And basically, you all know that reactive streams and reactive programming approach got a good fit for front-end development or reacting to user actions. So this is pretty similar. So the stream of actions from, for example, keyboard or controller right? On the other hand, if you're gonna look at the existing solution of Pacman game, we all seen that, for example, or if you have never seen, then you will see that the approach that is used is basically pull-based approach. For example, most implementation use while true loop in order to check what action happened from the user controller side. For example, we are collecting what actions were done from user side, and then we are trying to advance game based on that. Unfortunately, such approach won't be useful for distributed system or the case where we have remote communication between user client and user or action, for example, or game server. Because in that case, we are going to perform an action, and this action will be while true, so Pacman will be moved until go away at all. And our next action will be totally delayed, just in case, because this is real network. Therefore, if you're going to use push model, which is the essence part of streaming model, then we will be applying action only in case we observe that, right? This is really plain and straightforward approach. We don't have to do anything until we got this action. Therefore, we are going to advance it only when we got a real signal. All right. Oops, this is something wrong.
Do you need this?
All right. Let's take a look at some demo. Let's move to this slide. So basically, Reactive Streams is good because local hardware environment is fast, but we can't reapply it for network environment. Pacman controller is asynchronous streaming, so it has a good fit. So this approach has a good fit. And finally, it has, from Reactive Streams standard, we have a set of standard interfaces which really could be used in network communication as well as different libraries. For example, Reactive Streams offer us 3 main interfaces like publisher, subscriber, and subscription. And that's all you have to know and use in your game, for example. All right, let me show you some demonstration of that approach. For example, let's start from the explanation of what's going on in our application. So we have a few essence part of our solution. We have game client, game server. Game client is basically what we are going to observe in the browser. Game server is the main engine of all the actions. And we have our knowledge server, and we have our bot agent. So we are going to focus on the bot agent first. And we will be trying to build our series of movement and business logic in order to start somehow collecting knowledge and applying them. First of all, I would have to say that we have already pre-built some key learning algorithms, so we are not going to look into them into much details. And we are going to focus on how we can apply Reactive Streams approach in order to connect absolutely unrelated part of our distributed system in order to apply, for example, asynchronous gaining of knowledge and actions from remote service. First of all, let's start with decision service, because decision service is something which move or produce or precede our knowledge or learning. First of all, it could be anything. It could be, for example, you can connect your keyboard and you can play, for example, on your own in order to collect some knowledge and store them. Or it could be, for example, some random movement. It doesn't matter. The only thing that matters is that we are receiving flux of actions. It doesn't matter from which source. It could be absolutely different implementation, but the main point is that we are getting fluxes of decisions. Then we can easily combine this flux with other stages. For example, we can say, okay, then since we observed some action, let's send them to decision server, right? So we can easily say, okay, let's transform our pipeline and apply next stage, which is game engine service run. And we are sending to our game engine actions to perform, which could be local server or remote server, it doesn't matter. It's just series of actions. Afterwards, we can easily transform the next approach or next stage because our game server returns the series of outcome because game server is the main decision maker. So he says, okay, you perform this action, then you observe this outcome. And again, it doesn't matter. It could be local or remote. Everything is just representation of stream, of a synchronous stream. So then we perform learning service because we have to learn based on the outcome. And we say, okay, let's learn something from what happened. And then we can store this action. For example, if this is a really important action, and we can say, okay, let's transform again and say, okay, acknowledge service, acknowledge repository, educate. And that's it. Then we are going to call then, for example, in order to say, okay, void, because our API requires something to return, and that's it. Yeah, we have to say void. Yeah, mono void in that case. And that's it. So if we're going to run this, let's run this application. Pacman simulator, it's running. In this particular case, we are going to connect our application, and you will be able, so please welcome to this game server again. I'm going to share the link. And you will be able to see that right now, we are playing with a real Pacman, real Mrs. Pacman. So let me find her. Are you able to find Pacman? Somebody? Yeah, let's try to find it quickly. Nobody? No? Yeah, but it says that it's playing. Yeah. Yeah. As you can see, nobody is playing on behind the scene. So it's real Pacman. It works, right. And again, it restarted because this is the logic to restart, playing again and again and again until, I don't know, the end of time, or until I'm going to stop my game client, which means that it works, right? Looks good,
yeah.
but
it's still a bit slow. How can we
improve performance?
improve the performance?
So
Yes,
do you mean
so-
slow? It's because we are playing with the single game client.
That's
And
maybe
from
why
the
it's
implementation perspective, as we are going to see right now, we are using some knowledge repository, which is local knowledge repository, right? And it means that we have to run, for example, only a single client in order to produce some knowledge, and we will store this knowledge in memory, which is not useful,
Yeah,
right?
That's right, yeah. So
All right, so I know the solution for this case. Basically, since everything is a stream, we can easily distribute this stream on a separate service. So what we can do, so right now, we can create a couple of agents. And instead of trying to reuse the same memory, we can send the same stream of data or collect data from or information from our game server and store them and gain knowledge into the single knowledge server,
That's
right?
right,
Because we
yes,
have
yeah.
the same stream of actions and knowledge which could be stored everywhere or in a separate
It
machine.
is.
It doesn't have to be a single machine, which is super cool and
That's
will improve the performance of learning,
That's
right? So in that case, we're going to use RSocket because, as you might know, RSocket is a network protocol, and this is basically Reactive Streams as a network protocol. It could be used in absolutely different languages, environment. For example, you can create your knowledge service in C++ or JavaScript or whatever, any other language, and consume the same stream with the same behaviors. So we are going to use RSocket in order to connect to our game server, and we are going to send the result or a stream of knowledge to our remote knowledge server. That's what we are going to do. So let me show you how we can apply RSocket in order to kind of transparently continue our stream of knowledge to a separate machine. So let me go to my Pacman simulator. In order to start using RSocket, you have to use RSocket factory. You have to say, okay, since I'm going to behave as a client, I want to create a connection first. And then you have tons of options to do that. For example, you can say, this is keep alive. For example, you want to define some plugin, or you want to intercept, for example, your connection and somehow modify it. You can specify data MIME type. For example, as a client, you want to communicate over JSON or over protobuf or over whatever MIME type you want. And that's it. So there is a couple of useful tools and things built into the, for example, RSocket Java client. So you can define, for example, fragmentation, or just in case you got some interruption into the network, you can easily resume your stream as there nothing was between your client and server, which is super cool, and you don't have to write tons of business logic for that. So in our case, we have to say, okay, I want to define basically a scepter. No, I don't want to define that. I want to say, okay, I want to use efficient data sending. I don't want to copy object on sending, so I'm using zero copy approach from netty. And then I want to say, okay, I want to define my transport. And here we have like a couple of options. We can use TCP transport, or we can use WebSocket transport. It doesn't matter, since our server defined TCP endpoint, we are going to use TCP client transport, and we are going to say, okay, we want to connect to the port, but to which port? So let's go and look at our knowledge server. Our knowledge server is using Akka, so you can use any reactive streams library for that purpose. And our server define the processing of data using, for example, Akka streams. Everything is reactive streams, so Akka streams is valid as well. And here we define our server, and in that case, we are using port, which port we are using? Oh yeah, we are using 9099. So we are going to connect to the port 9099, and we are going to connect to DynaMan, since we are going to use the remote real server, which is running on our machine. Okay, that's what we have to do. Finally, what you have to say, okay, start and block, since we want to wait until the connection and start using given RSocket. As I said before, RSocket is not only streaming. It gives you different communication patterns, so you can use request response, request stream, or request channel, and just say send a publisher of payloads. And in this case, we are using RSocket RPC in order to utilize protobuf RPC and all this cool feature from protobuf messaging. That's why I have like RSocket RPC in my project, and I'm going to use just a particular generated interface for that purpose. All right, then I have this remote knowledge repository, and instead of using in-memory knowledge repository, I'm going to use that one, and that's it. I don't have to rewrite anything. I'm using reactive streams, so even though this is remote service, I'm going to asynchronously send data without blocking my application, which will be almost the same, right?
That's right.
Okay, let me run this again, and again, and again, and many, many times, in order to make sure that right now we are having not single Pacman player, but a couple of them. Yeah. So seems that all of them are playing. Not yet. They are starting, compiling something. Yeah, starting. This one is playing, I guess. Yeah, this one is playing, this one is playing. Perfect. Right now we should have 2, 3, or even more Pacman playing at the same time and collecting knowledge. They are separate knowledge to the same knowledge base, which is super cool, right?
That's right, yes. So,
all right, seems to be working.
that's right.
So let's summarize.
Sure. Okay, so basically we've demonstrated using reactive streams, and basically using reinforcement learning is a really good model. Using this case-based reasoning too, then it's less technique for continuous learning in this
Right.
case. Yeah, okay. And it fits very well too for like online Pacman, as you can see. And also, too, the lines of code is actually quite simple in this case when you use RSocket.
Yeah, as we have seen, we don't have to rewrite everything in order to switch from local environment to distributed environment. Reactive streams can be used for synchronous communication or synchronous data streaming, as well as for distributed asynchronous data streaming. It's a very good approach to send your data over several environments without like changing and rewriting code a lot. Right? This is the same stream over the wire or over the single machine. It doesn't matter.
That's correct. And it works very well locally, that's you just described to, as well as in distributed environment.
All right.
Yeah.
So maybe you can recommend something to learn for those who are curious about machine learning.
Yeah, sure. So some resources we have, for example, you can check the reactive streams, and this is the URL. Then there's also Reactive Foundation, which Oleg could talk about it in your session before this, the Reactive Foundation. And then we also, too, when we were doing this research, we looked up this book, too, is the Machine Learning, Reinforcement Learning, Artificial Intelligence, A Modern Approach. This actually specifically is the chapter 21 that talks about reinforcement learning, very useful by Stuart Russell and Peter Norvig. Then there's also a reinforcement learning and introduction by Richard Sutton and Andrew Bartow.
So this is basically the paper that we used in order to build our agent.
Agent, yeah. So actually, then this will be this particular paper.
Yeah.
This one is basically from there's a research paper too that talk about the case-based approach in here. So, and then some more additional resources is that because I work for IBM, and so we'd like to just invite you to sign up for the IBM Cloud if you haven't already done so. We kind of have intention too, because it's our first time doing this, first 2 months of doing this. So we have yet to have chances to actually put it onto the IBM, into our cloud platform. We can deploy this server onto our cloud platform, so that will be our next presentation. But otherwise too, we'd like to invite you to sign up for the IBM Cloud. So this is the URL that you can use up there. And then
and if you are curious about the implementations that we have shown during this presentation, there is a last link, so please visit GitHub repository and you will find all the information related to this presentation and to this application.
That's right. So that's the GitHub, yeah, it's the third link.
Yeah. All right, I guess this is basically it. If you got any question, you are more than welcome to ask it. And if you don't have anything, thank you for your attention.
Yeah, thank you again for coming to our talk. Yeah, thanks.
Any questions? All right. Yeah. So if you don't have any question, have a good conference and have a nice day and evening.
That's right, yeah. Oh, that's right. There are also some meetups too, I think. Right? Yeah, we should also remind.